Where did the universe find the recipe for life itself? We are about to journey through 30 of the most compelling theories for the origin of the first organic molecules. You will discover a mix of established science and radical new ideas that completely reshape our understanding of life's cosmic beginnings. We will explore whether life was sparked by lightning in a primordial soup, or if it hitched a ride to Earth on a comet. How could deep-sea vents or even interstellar ice create the foundations of biology? By the end, you will see the universe not as a void but as a master chemist. What single idea about our origins feels most true to you? The first great theory began not in space but right here at home. In the 1920s, two scientists, Alexander Oparin and J.B.S. Haldane, proposed a radical idea. They envisioned an early Earth cloaked in a thick atmosphere of methane, ammonia, water vapor, and hydrogen. This was the primordial soup. In this chaotic chemical kitchen, they suggested energy from relentless lightning strikes, the sun's harsh ultraviolet rays, and the planet's own volcanic heat could have acted like a cosmic chef, stirring these simple ingredients into something far more complex. The energy would have broken the simple molecules apart, allowing their atoms to recombine into the building blocks of life, the first amino acids. For decades, this remained a compelling but unproven idea. Then, in the 1950s, a young graduate student named Stanley Miller and his professor, Miller-Urey, decided to test it. They built a remarkable apparatus, a closed loop of glass flasks and tubes designed to mimic the ancient Earth. One flask held water for the early ocean, another was filled with the proposed primordial gases. Then they sent sparks of artificial lightning cracking through the gaseous mixture. The results were stunning. After just 1 week, the once clear water had turned a murky pink and brown. When Miller analyzed this liquid, he found it was rich with amino acids, the fundamental components of proteins. It was a monumental discovery. The Miller-Urey experiment seemed to show that the basic ingredients for life could form with shocking ease under early Earth conditions. This theory became the cornerstone of origins of life research for a generation. It painted a powerful picture of our planet as a self-made cradle of life. But as science advanced, questions began to surface. The main critique centers on the recipe itself. Did Earth's early atmosphere truly contain the right mix of gases, the methane and ammonia that Miller and Urey used? Many geochemists now believe the atmosphere was likely more neutral, composed of carbon dioxide and nitrogen, gases far less likely to jumpstart the chemical reactions needed. And then there is the grander puzzle. Creating amino acids in a flask is one thing, but that is a far cry from building the intricate structures of RNA, DNA, and living cells. How do you go from a handful of organic bricks to an entire, self-replicating cathedral? The primordial soup theory gave us a vital first chapter, but it left the rest of the book unwritten, forcing scientists to look for other answers, perhaps even beyond our world. This search for a new kitchen led scientists to gaze upward into the cold expanse of space. If the recipe was not perfected on Earth, perhaps it was delivered. This is the captivating theory of Panspermia, the idea that life's raw ingredients, or even life itself, hitched a ride to our planet on a cosmic delivery service of comets and asteroids. Imagine a tiny, resilient microbe or a complex organic molecule, frozen for millions of years within a protective rocky shell, journeying between the stars. It is a grand vision that completely reframes our origins, suggesting that Earth was not the chef, but merely the diner at a galactic feast. There are different flavors of this idea. The most widely discussed is lithopanspermia, where life is transported inside rocks. A massive impact on one world, like Mars, could blast debris containing hardy microorganisms into space. These rocky capsules then drift for eons, shielding their precious cargo from radiation, until they are captured by another world's gravity and fall as meteorites seeding a new planet. Then there is the more speculative concept of directed panspermia, which proposes that an advanced alien civilization intentionally sent the seeds of life to worlds they deemed suitable. While this remains firmly in the realm of science fiction for now, it highlights the profound shift in thinking that panspermia represents. The most compelling evidence for this cosmic delivery service comes from the heavens themselves. In 1969, a meteorite fell near the town of Murchison in Australia. When scientists analyzed its dark, carbon-rich stone, they made a stunning discovery. It was loaded with amino acids, the same building blocks that Miller and Urey created in their flask. But the Murchison meteorite contained over 90 different types, a far more diverse set than the early Earth experiment produced. This was not a simulation, this was real. The universe had sent us a sample, and it was brimming with the very ingredients we associate with life. This single rock provided powerful proof that the fundamental chemistry for biology is not unique to our planet, but is happening naturally across the cosmos, written into the very fabric of star systems. Panspermia elegantly solves the problem of a hostile early Earth by moving the kitchen elsewhere. It suggests that the long, complex process of creating life's precursors could have begun in the calm, frozen clouds of interstellar space, or on a more chemically active world like a young Mars. Our planet then simply received a carefully packaged starter kit. This transforms the search for life from a planetary endeavor into a galactic one. It implies that we are all potentially connected, that the spark which ignited biology on our world may be the same spark that flickers on countless others. Yet for all its grandeur, panspermia does have a catch. It does not actually answer the ultimate question of how life began, it merely relocates it. If life arrived here from Mars, then how did it start on Mars? If it came from a comet, how did those complex molecules form in the deep freeze of space? The mystery is not solved, it is just moved to a new, even more spectacular stage. So if the kitchen was not in the sky or on the surface, where else could it be? The answer may lie in the most alien landscape on our own planet, a place of crushing pressure and eternal darkness. In 1977, scientists piloting the submersible Alvin made a discovery that shattered our understanding of where life can thrive. On the deep ocean floor near the Galapagos Rift, they found hydrothermal vents. These are not simple hot springs, but colossal, chimney-like structures billowing superheated, mineral-rich water into the frigid blackness. And surrounding them was a stunning oasis of life with giant tube worms, ghostly white crabs, and strange clams, all flourishing in a world without a single ray of sunlight. This discovery proved that life does not need the sun. It can be powered by chemistry and geothermal heat alone. This revelation sparked a revolutionary theory. Perhaps these deep sea vents were not just a biological curiosity, but the actual cradle where life first began. The most compelling version of this is the alkaline vent hypothesis. Imagine a porous, rocky structure like a natural sponge towering from the seafloor. Inside its microscopic pores, water heated by the Earth's magma reacts with minerals like olivine, a process called serpentinization. This reaction does two remarkable things. First, it makes the water highly alkaline, and second, it releases hydrogen gas. This hydrogen is a potent fuel, a ready food source for early chemistry. The vent structure itself becomes a catalyst, its mineral walls providing perfect surfaces for carbon and hydrogen to meet and form more complex chains, the first organic molecules. But the real magic lies in a fundamental force of nature. The alkaline fluid inside the vent is rich in positively charged particles called protons, but it has far fewer of them than the acidic ocean water outside. Nature abhors an imbalance, and this difference creates a powerful, natural gradient, a kind of chemical pressure, as protons desperately try to flow from the acidic ocean into the alkaline vent to even things out. This is not just a flow of water, it is a flow of energy, a natural battery built into the geology of the planet. And here is the breathtaking connection. Every living cell on Earth today, including every one of your own cells, runs on this exact same principle. Tiny molecular machines in your cell membranes pump protons to create a gradient, and then harness the energy as those protons flow back in like water turning a wheel. The alkaline vent theory suggests that the first life forms did not have to invent this complex machinery. They simply plugged into a power grid that was already running, using the natural proton gradient of the vent to fuel their first steps toward metabolism and growth. These rocky labyrinths offered the perfect nursery, safe from the violent asteroid impacts and deadly ultraviolet radiation that sterilized the early Earth's surface. Here in the deep, dark quiet, protected within tiny rock pores bathed in a constant flow of energy and chemicals, the first organic molecules could have assembled, experimented, and slowly, over immense stretches of time, learned how to become life. It paints a profound picture of our origins, not in a sunlit soup, but in the warm, chemical embrace of the deep ocean, powered by the very heart of the Earth. Yet the deep sea vents are not the only place where nature performs its chemical magic. Our search for the first organic molecules must venture into an environment even more extreme, the frigid void between the stars. Drifting within vast, dark molecular clouds are countless specks of dust, each one smaller than a particle of smoke. In the deep cold of space, just a few degrees above absolute zero, these tiny grains become cosmic refrigerators. They accumulate frosty coatings of ice, not just water ice, but frozen layers of simple molecules like carbon monoxide, ammonia, and methane. To our eyes, these clouds are just empty blackness, but to a chemist they are immense silent laboratories. Here, the building blocks of life are not forged in fire, but in ice. The process is one of surface chemistry. Individual atoms and simple molecules floating in space slowly bump into these icy dust grains and stick, held fast by weak chemical bonds. They are frozen in place, a captive audience for the universe's next act. That act is driven by two powerful forces, the relentless sleet of cosmic rays, high-energy particles shooting across the galaxy, and the subtle glow of ultraviolet light from nearby stars. This radiation provides the spark. When a cosmic ray or a photon of light strikes the icy mantle, it blasts the frozen molecules apart, creating a soup of highly reactive fragments and radicals. Trapped together on the surface of the grain, these broken pieces have nowhere to go. They bump into each other, recombining in new and more complex ways. A simple carbon monoxide molecule might link with a hydrogen atom, then another, slowly building up toward more interesting compounds. Over millions of years, this slow-motion dance on a microscopic stage can create molecules of startling complexity, including amino acids and the nucleobases that form the letters of our genetic code. This is not just a theory. We have seen the spectral signatures of these complex organics in space, and we have held the evidence in our hands. The Murchison meteorite and others like it contain a rich inventory of molecules that scientists can now recreate in laboratories by simulating the conditions of interstellar ice. They take a metal plate, cool it to near absolute zero, deposit a layer of simple ices, and then bombard it with radiation. The result is always the same, a sticky, organic goo known as tholins, a precursor to the chemistry of life. This means the universe is not a sterile void. It is a prolific factory, quietly manufacturing the ingredients for biology on a galactic scale, long before planets even form. These icy grains, eventually drawn together by gravity to become comets and asteroids, would have rained these pre-made organic molecules down on the young Earth. So the very ice that seems so hostile to life may, in fact, have been its cosmic nursery, proving that the coldest places in the universe can hold the warmest potential for life. But what if the energy for life came not from the sky or the sea, but from deep within the rocks beneath our feet? Another theory points to the very ground of the early Earth, where natural radioactive elements like uranium and potassium-40 were abundant. Their slow, relentless decay provided a completely different kind of power. Unlike a lightning bolt's sudden flash, radioactive decay is a patient, persistent drummer, beating out a steady rhythm of energy for millions of years. This was not a violent shock, but a gentle, constant warmth. Imagine water percolating through mineral-rich clays or trapped in porous rocks deep underground, far from the chaotic surface. As radioactive atoms in the surrounding rock decayed, they would have released energy in the form of heat and also a stream of particles like alpha and beta radiation. This radiation, striking the water and dissolved gases, could have broken molecules apart, creating a soup of reactive fragments ready to recombine. The real advantage here is time and stability. A lightning strike is over in an instant. A deep sea vent can shift and disappear, but a radioactive beachhead offers a quiet, protected laboratory that remains chemically active for eons. In these secluded aquifers, bathed in this low-level energy, simple carbon-based molecules could have slowly, patiently built complexity, link by link. Scientists have tested this in labs, irradiating water and simple gases, and have successfully produced amino acids and the components of RNA. This paints a picture of life's beginnings not in a dramatic, explosive event, but in the profound quiet of the subterranean world, powered by the faint, ancient heartbeat of the planet itself. There is a profound paradox at the heart of creation, where absolute destruction gives birth to something new. We often see asteroid impacts as apocalyptic events, and for the dinosaurs, one certainly was. But for the earliest Earth, these violent collisions may have been the universe's most forceful act of chemistry. This is impact shock synthesis, a theory that recasts planetary bombardment not as a scourge but as a crucible. The physics is staggering. When a large comet or asteroid slams into a planet, it does not just make a crater. It compresses the atmosphere and the ground in front of it to an unimaginable degree, creating a fleeting bubble of immense pressure and searing heat. For a fraction of a second, temperatures can soar to thousands of degrees, and pressures can exceed those found deep inside the Earth. Within this temporary inferno, simple, stable molecules are shattered. Atoms of carbon, nitrogen, and hydrogen, ripped from their comfortable bonds, are forced into frantic new alliances. Then, as the shockwave passes and this superheated bubble rapidly expands and cools, these newly formed complex molecules freeze in place, preserving them from destruction. It is a bit like forging a sword, using a sudden, tremendous blast of heat and pressure to transform raw, simple iron into hardened steel. The beauty of this theory is its dual nature. An impactor does not just deliver pre-made organic compounds if it is a carbon-rich asteroid or comet. The collision itself becomes a chemical factory, synthesizing new organic molecules right on the spot from the planet's own raw materials. A comet composed mostly of ice and dust slamming into an atmosphere of carbon dioxide and nitrogen could, in that single flash of violence, manufacture a shower of amino acids that rain down onto the young planet's surface. Scientists have tested this dramatic idea in the lab using powerful guns that fire projectiles at incredible speeds into gas mixtures designed to mimic the early Earth's atmosphere. The results are unequivocal. These simulated impacts consistently generate a suite of amino acids and even the nucleobases that form the backbone of RNA and DNA. It is a compelling demonstration that the very same energy that can sterilize a world can also, in the right context, provide the spark for life's ingredients. This theory weaves together several earlier ideas into a single cataclysmic event. It incorporates the delivery concept of Panspermia, the energy source of the primordial soup, and the rapid synthesis of complex chemistry. It suggests that our planet's most violent era, the late heavy bombardment, was not a barrier to life's emergence, but possibly its catalyst. Each world-shattering impact could have seeded the oceans with a fresh infusion of organic building blocks, churned into the primordial soup by the very force that brought them. So while we rightly fear the destructive power of asteroids, we might also owe them a debt of gratitude. They may have been the chaotic, unforgiving blacksmiths that forged the first fragile links in the chain of life. While asteroids were hammering the young Earth, a far more delicate chemistry was unfolding in the skies of other worlds. High above a planetary surface, bathed in the unfiltered light of a young sun, simple gases can perform a ballet of creation. This is the theory of atmospheric photochemistry, and it expands the stage for life's ingredients to countless planets and moons across the galaxy. Picture the atmosphere of a world like Saturn's moon Titan, a thick orange haze of nitrogen and methane. Here, the sun's ultraviolet radiation acts not as a destroyer but as a master sculptor. A single photon of UV light carrying immense energy smashes into a methane molecule, shattering its atomic bonds. The resulting fragments, known as radicals, are wildly reactive, desperate to form new connections. They collide with nitrogen molecules and with each other, setting off a cascade of reactions. This chain of events builds molecules of increasing size and complexity, link by link, eventually forming vast clouds of organic aerosols that drift down through the atmosphere like a slow cosmic snow. These are not the simple bricks of life, but something arguably just as important, a rich, tarry substance of countless carbon-based compounds, a prebiotic haze that could coat a world's surface with potential. We are not merely speculating about this process. The Cassini spacecraft, which orbited Saturn for 13 years, provided stunning confirmation. Its instruments peered through Titan's opaque atmosphere and detected these very compounds, a complex organic chemistry unfolding on a moon far from the sun's warmth. This tells us something profound. The process that might have contributed to life on Earth is not unique. It is a universal recipe requiring only a thick atmosphere and the light of a star. Any world with a similar gaseous shroud could be manufacturing these organic building blocks right now, painting its skies with the faint chemical signature of life's possibilities. This transforms our view of the cosmos. We are no longer just looking for planets that resemble Earth. We can now search for worlds shrouded in orange haze, knowing that within those clouds the universe might be quietly, constantly cooking. Amidst the chaos of lightning strikes and impact shocks, perhaps life needed a moment of quiet organization. Another theory suggests the first complex molecules were not brewed in a turbulent soup, but meticulously assembled on a solid, structured surface. This is the compelling idea of clay mineral catalysis. Imagine the surface of a common clay like montmorillonite under a powerful microscope. You would not see a smooth, flat plane, but a landscape of repeating geometric patterns, a crystalline lattice of atoms arranged in a perfect, orderly grid. This structure is not passive. The surface of the clay carries a subtle electrical charge, acting like a powerful magnet for the loose, simple organic molecules drifting in the water around it. These building blocks, like amino acids or the components of RNA, are drawn to the clay and become tightly concentrated along its surface, held in place and arranged by the mineral's invisible template. This concentration is the first critical step. In a vast, dilute ocean, the chance of two specific molecules meeting and reacting is incredibly slim. But on the surface of a clay particle, they are brought into intimate contact, a molecular party forced into a tiny, crowded room. Then the clay does something even more remarkable. It acts as a catalyst. The very chemistry of its surface can help strip away water molecules that form when two smaller molecules try to link together into a longer chain, a process called polymerization. It effectively gives the molecules a gentle nudge, lowering the energy required for them to bond. This is not a violent, high-energy reaction, but a patient, guided assembly. Scientists have demonstrated this process in the lab, showing that clays can indeed facilitate the formation of chains of RNA. The molecule many believe was the first self-replicator from its simpler building blocks. The clay provides both the scaffolding and the tools, a natural, non-living factory for creating order from chaos. This theory builds a powerful and elegant bridge between the non-living world of rocks and minerals and the living world of biochemistry. It suggests that the path to life was not a sudden, miraculous leap, but a gradual, step-by-step process where geology provided the stage, the script, and the director, guiding simple chemistry toward the profound complexity of biology. The very ground beneath our feet, the most common of dirt, may have held the architectural blueprint for life itself. The quiet, patient assembly on clay surfaces offers one path from chemistry to biology. But what if the first life did not just sit on a surface, it ate the surface itself? This is the provocative iron-sulfur world hypothesis proposed by the chemist Günther Wechtersheuser. He envisioned a radically different cradle of life, one where the very first organisms were not free-floating cells, but a living film, a two-dimensional coating on a mineral surface. The stage for this drama is the same hydrothermal vent system, but the main actor is a specific mineral, iron pyrite, also known as fool's gold. Wechtersheuser's brilliant leap was to propose that the first energy source for life was not sunlight or proton gradients, but a simple, powerful chemical reaction, the formation of pyrite itself. When hydrogen sulfide, which billows from volcanic vents, reacts with iron ions present in the rock, it creates iron pyrite and releases a burst of chemical energy. He proposed that this exothermic reaction, this act of a mineral crystallizing into existence, could have been harnessed by the earliest metabolic cycles. Imagine a tiny, sheltered cavity on a bubbling vent, its walls coated with a glistening layer of fresh pyrite crystals. This crystalline surface, with its positively charged, orderly structure, would have acted as a powerful magnet and a catalyst, drawing in carbon dioxide from the surrounding water. Using the energy released from making more pyrite, this surface could have driven a process called carbon fixation, stripping carbon atoms from carbon dioxide and linking them together into ever more complex organic chains. In this view, the very first life form was not a cell, but this self-sustaining, two-dimensional chemical reaction, a metabolic system literally stuck to the rock that was both its home and its food source. This surface-based life would have slowly built up its complexity, creating a rich organic layer on the pyrite, a kind of primordial lichen that was part rock and part chemistry. Only later, according to this theory, did this film learn to surround itself with a membrane and bud off, becoming the free-living, three-dimensional cells we recognize as life today. It is a strange and powerful image, suggesting our earliest ancestor was not a creature, but a chemical process, a hungry, growing stain on a crystal of fool's gold, powered by the slow, steady formation of a mineral deep in the eternal night of the ocean. Even as we look to the ground or the deep sea, the cosmos continues its relentless assault. From the farthest reaches of the galaxy, a constant drizzle of high-energy particles rains down upon every world, every moon, every drifting cloud of gas. These are cosmic rays, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light. Their power is immense, far greater than ultraviolet light, allowing them to penetrate deep into atmospheres, into surface ices, and even into the upper layers of rock. This is not a gentle energy source, it is a sledgehammer, and in its wake it can leave behind the very structures life requires. This is cosmic ray-induced polymerization, a theory that casts these particles as universal chemists. When one of these high-energy bullets smashes into a collection of simple organic molecules called monomers, the effect is explosive. It blasts through the material, tearing electrons from atoms and creating a wake of intensely reactive fragments. These charged fragments, or radicals, are desperate to form new bonds. In the chaotic instant after the cosmic ray's passage, they violently reconnect, not just into their original forms, but into new, more complex chains. A single amino acid monomer might link to another, and then another, forging a protein-like polymer. a simple sugar might be woven into a longer carbohydrate chain. The cosmic ray provides the immense, localized energy required to overcome the barriers that normally prevent these spontaneous connections. The genius of this process is its universality. It works in the frozen emptiness of an interstellar ice mantle, where the resulting polymers are frozen in place until they become part of a comet. It works in the upper atmosphere of a planet, creating complex organic hazes that slowly drift down to the surface. It even works on the barren, airless surface of an asteroid, tirelessly processing the carbon-rich dust grains for billions of years. Laboratory experiments confirm this profound capability. Scientists expose frozen mixtures of water, ammonia, and methanol, mimicking interstellar ice, to radiation that simulates the galactic cosmic ray environment. The result is never a simple residue. Instead, they find a complex, tar-like substance rich with polymerized chains, a simulated prebiotic goo created by pure particle energy. This suggests that wherever simple organic molecules can accumulate, cosmic rays are there to work on them, acting as a relentless galactic-scale driver for chemical complexity. It means that the path to life's first large molecules may have been paved by the most violent and abundant energy source in the universe, a silent, invisible rain that has been falling since the first stars were born. The violent rain of cosmic rays was not the only force at work in the young solar system. To find the true origin of our planet's organic wealth, we must travel back further, to the very dust from which our world was born. Before there was an Earth, before there were planets at all, our entire solar system was a vast, swirling disk of gas and dust orbiting a newborn star. This was the solar nebula, a chaotic, luminous cloud stretching billions of miles across. Within this colossal nursery, the fundamental chemistry for life was already being written. As the disk slowly cooled from its initial inferno, a symphony of chemical reactions began. In the warmer, gaseous inner regions, individual atoms collided and combined in what are known as gas phase reactions. A carbon atom might meet a hydrogen atom to form methylidyne, a simple but reactive radical that could then link with nitrogen or oxygen, building molecular complexity step by step right in the void. But the most profound chemistry happened on solid ground, or more accurately, on the surfaces of microscopic dust grains. These tiny particles acted as cosmic platforms, the universe's first laboratories. Individual atoms and molecules drifting aimlessly in the gas would stick to these cold, solid surfaces. Once trapped together on a single grain of dust, they were no longer lonely drifters. They became a captive audience, forced into close proximity where they could react. A hydrogen atom could shuffle across the surface to meet a carbon monoxide molecule, creating formaldehyde. An oxygen atom might link with hydrogen to form water ice. This slow, patient dance, known as grain surface chemistry, built layers of frozen, complex organics on countless trillions of dust specks. Over thousands of years, these icy mantles grew, creating a frozen repository of prebiotic material. Then gravity took over. These organic, rich dust grains began to clump together, forming pebbles, then rocks, then mountain-sized planetesimals. The very comets and asteroids that would later bombard the Earth were, in their essence, colossal aggregations of these primordial, chemistry-laden dust grains. This means that the ingredients for life were not an afterthought added to a finished planet. They were baked into its foundation, a fundamental part of the recipe from the very first moment. When the Earth finally coalesced from this material, it was already pregnant with organic potential. The solar nebula did not just give us a world to live on, it provided the entire chemical starter kit for life itself, proving that our biological story began not in a primordial soup, but in the dust of a long-vanished star. That cosmic dust and ice from the solar nebula had to end up somewhere, and for Earth, that delivery came in a firestorm of comets. This brings us to a powerful synthesis of ideas, a theory that combines the cosmic delivery of panspermia with the transformative violence of impact synthesis. Imagine a comet, a colossal mountain of ice and dust, already packed with a rich inventory of simple organic molecules forged in interstellar space. It streaks through the early solar system, a frozen arc carrying the universe's potential. Then it crosses paths with a young, water-rich Earth. The collision is cataclysmic, releasing energy equivalent to millions of nuclear bombs. In that single, shattering instant, the comet is vaporized. But this is not the end of the story. It is the beginning of a new chapter. The incredible heat and pressure of the impact do not merely destroy the comet's precious cargo, they repurpose it. The simple organics within the ice, the amino acids and nucleobases, are shattered into even more reactive fragments. As the fireball expands and cools, these fragments are thrown into a chaotic, high-energy mixer along with the gases of the comet and the planet's own atmosphere and water vapor. In this temporary chemical reactor, lasting only minutes, the broken pieces violently recombine. They are not just reforming into what they were, they are building new, more complex and diverse molecules than existed before. A simple amino acid might link with another, forming a short chain. A nucleobase might attach to a sugar like ribose. The impact acts as a universal chef, using the comet's organics as its core ingredients and the planet's raw materials as its spices, cooking up an entirely new, more sophisticated menu of prebiotic compounds. Then comes the perfect environment for the next step. The energy of the impact excavates a vast crater, and as the planet's crust rebounds, it creates a central peak. Water vapor from the impact condenses and falls as rain for centuries, slowly filling the crater to form a warm, sheltered lake. Into this newly formed pond rains a concentrated shower of the newly synthesized, complex organic molecules, all deposited together in one place. This is not a dilute, planet-wide ocean where molecules rarely meet. This is a highly concentrated, diverse prebiotic soup, a perfect nursery where these new chemical inventions can interact, mix, and experiment with each other. The comet did not just deliver a starter kit. It delivered the ingredients and then used its own destructive impact to build a fully stocked, state-of-the-art kitchen, complete with a protected workshop for the next steps. This theory elegantly solves the problem of concentration and diversity. It provides a localized environment teeming with a wider variety of complex molecules than any single process could likely produce, all gathered in a single body of water, shielded from surface radiation, and kept warm by the residual heat of the impact itself. Our planet, its most violent moments may have created thousands of these fertile crucibles, each one a potential birthplace where chemistry could finally cross the threshold into biology. But what if the very first life form was not a chemical reaction or a chain of molecules, but a tiny, self-made bubble? This is the lipid world hypothesis, a theory that shifts our entire focus away from proteins and RNA to the humble, oily molecule of the lipid. Imagine a lipid not as a mere building block, but as an architect. Certain lipids have a remarkable property. One end of the molecule is attracted to water while the other end repels it. When enough of them are floating together in water, they spontaneously arrange themselves into a perfect, stable sphere, a hollow vesicle with a protective, double-layered wall. This is not just a chemical curiosity. This is the birth of a boundary, the invention of the very first cell membrane. These lipid vesicles become the universe's first private rooms, creating an inside and an outside. Within their protective embrace, other organic molecules could be safely concentrated, shielded from the dilute and chaotic outside world, but the magic does not stop there. These structures are dynamic. If more lipid molecules are available in the environment, they can incorporate themselves into the vesicle wall, causing the entire bubble to grow. As it grows larger and its membrane becomes unstable, it can spontaneously divide, pinching off into two or more daughter vesicles. This is a primitive form of reproduction, a self-replication driven not by genetic code, but by simple physics and chemistry. Now envision a scenario where a growing lipid vesicle happens to encapsulate a handful of molecules that can perform a simple energy-releasing reaction, a rudimentary metabolism. This vesicle now has a distinct advantage. It can use that internal energy to grow and divide more efficiently than its neighbors. Through this process, a form of selection emerges. Vesicles that accidentally trap useful chemical cycles become more successful, thriving and multiplying, while empty or less efficient bubbles fade away. This lipid world presents a compelling pathway. It suggests that the fundamental unit of life, the cell itself, could have emerged first, providing a stable container within which the more complex machinery of genetics could later evolve. Before there was an instruction manual, there was the house, a simple, self-assembling, self-replicating bubble that gave the chemistry of life a place to call home. While lipids could form the walls of the first cells, they could not build the machinery inside. For that, life needed a master architect, a chemical element capable of linking molecules together into the complex blueprints of DNA and the energy currency of ATP. That element is phosphorus. On the early Earth, however, phosphorus presented a paradox. It was abundant, but almost entirely imprisoned within insoluble minerals like apatite, the same rock that makes up our tooth enamel. Locked in this crystalline form, phosphorus was chemically inert, unable to react with the organic molecules drifting in the primordial waters. It was as if life had all the lumber to build a house, but no nails. The solution to this chemical lockdown may have arrived from the sky. Meteorites, particularly iron-rich ones, often contain a rare and remarkable mineral called schreibersite. Unlike its terrestrial cousins, schreibersite is highly reactive. When it comes into contact with water, it corrodes, releasing phosphorus in a soluble, chemically active form that is desperate to bond with other molecules. In the laboratory, when scientists place schreibersite in water with simple organic compounds like glycerol, a fascinating reaction occurs. The phosphorus atoms readily attach themselves to these organics, creating phosphorylated molecules. This process, known as phosphorylation, is the exact same chemical step that nature uses to build the backbone of DNA and to power every cell in your body with ATP. A single meteorite bearing this mineral could have dissolved in a warm pond, unleashing a wave of reactive phosphorus that began stitching the available organic soup into more sophisticated structures. This theory elegantly solves one of the most stubborn bottlenecks in the origin of life. It suggests that the final, crucial piece of the puzzle, the element that bridges simple chemistry and complex biology, was a gift from the cosmos, delivered by the very same impacts that may have forged our planet's first organic compounds. While the deep sea offered protection, the young continents were brewing their own recipe for life. Far from the crushing pressure of hydrothermal vents, vast geothermal fields and bubbling hot springs created a dynamic stage for prebiotic chemistry. These terrestrial laboratories provided a completely different set of advantages. Picture a volcanic landscape where rainwater collects in shallow, mineral-rich pools heated from below by the Earth's magma. These pools are not static. They undergo a constant rhythmic cycle, filling with water during rainstorms and then slowly evaporating under the sun or geothermal heat. This cycle of wetting and drying is a chemical engine. As the water evaporates, every organic molecule dissolved within it becomes dramatically concentrated. Amino acids and other building blocks, once drifting far apart in a vast ocean, are now squeezed together, dramatically increasing their chances of meeting and reacting. This is not a gentle suggestion, it is a forced assembly. The process does more than just concentrate ingredients. The act of drying itself can directly drive chemical bonds to form. When two amino acids link to create a dipeptide, a molecule of water is released as a byproduct. In a flooded pool, this reaction is reversible as the surrounding water pushes the molecules apart. But in a drying pool, that released water immediately evaporates away, pulling the reaction forward and locking the new bond in place. Over countless cycles, this simple process could have built not just short chains, but long, complex polymers, the ancestors of proteins and RNA. The surrounding environment adds another critical ingredient, a diverse toolkit of mineral catalysts. The rocks and clays in these geothermal areas are rich in elements like zinc, copper, and manganese. As the hot, mineral-laden water circulates through the ground, it leaches these elements into the pools. These metals can act as powerful catalysts, their unique chemical structures providing a perfect surface to guide and accelerate specific reactions, potentially helping to assemble the intricate nucleotides of the first genetic material. This entire environment also offers a natural pathway to encapsulation. The same lipids that can form vesicles in the deep sea will also do so in these warm ponds. As the pool dries, these fatty molecules will be pushed together, spontaneously organizing into multilayered membranes and micelles, trapping the newly formed polymers inside. When the next rain comes and refills the pool, these primitive protocells would be released back into the water, now carrying a concentrated payload of complex molecules within a protective shell. This creates a stunningly complete cradle. The geothermal field provides the energy through its heat. The wet-dry cycle provides the mechanism for concentration and polymerization. The minerals provide the catalytic tools, and the environment naturally assembles the first cellular compartments. It suggests a world where life could have emerged not in one single perfect location, but in thousands of steamy, bubbling ponds across the young continents, each one a potential birthplace where chemistry patiently built its way toward biology. Yet all these theories face a monumental puzzle, a classic chicken and egg dilemma. Which came first, the metabolic machinery that sustains life or the genetic code that instructs it? One powerful idea proposes a single, elegant solution. This is the RNA world hypothesis, a vision of a time before DNA or proteins, when a single, versatile molecule ruled the early Earth. RNA, or ribonucleic acid, is the hypothesized hero of this ancient era. It possesses a unique and almost magical duality. Like DNA, it can store genetic information in the sequence of its building blocks, acting as a blueprint that can be copied and passed on. But unlike the relatively inert double helix of DNA, RNA can also fold into intricate, three-dimensional shapes that allow it to act like a protein, catalyzing specific chemical reactions. In this scenario, one molecule could be both the software and the hardware, the instruction manual and the factory worker building the product. The first life forms in the RNA world would have been simple, self-replicating RNA strands. A molecule would act as a template, attracting complementary building blocks from the environment and stitching them together to create a copy of itself. These copies would then do the same, initiating a primitive form of Darwinian evolution where the most efficient and stable replicators would come to dominate the chemical landscape. The most compelling evidence for this theory emerged in the 1980s with the stunning discovery of ribozymes. These are natural RNA molecules that function as enzymes, catalyzing vital biochemical reactions. We have found ribozymes that can cut and join other RNA strands, and most significantly, one found in modern cells that helps build proteins, has a core made entirely of RNA that is responsible for its catalytic power. This ribozyme is like a living fossil, a molecular relic from the RNA world still operating at the heart of all life today. For all its elegance, however, the RNA world faces its own profound challenges. How did the first RNA molecules form without biological help? RNA is a complex polymer, and its individual building blocks, nucleotides, are notoriously difficult to create under plausible prebiotic conditions. Furthermore, RNA is a fragile molecule, easily broken down by water or radiation. How could such a delicate chain have survived long enough to begin the process of self-replication? The RNA world may not be the final answer, but it provides a crucial and compelling framework. It suggests that the path to life was simplified by a molecule that could do it all, a jack of all trades that eventually, and perhaps reluctantly, specialized its functions, delegating information storage to the more stable DNA and chemical catalysis to the more versatile proteins, laying the foundation for the biological universe we know. The profound challenge of the RNA world leads us to an even more fundamental puzzle, one written into the very fabric of our bodies. Every living thing on Earth is built from molecules that have a distinct handedness. The amino acids that form our proteins are exclusively left-handed, while the sugars that form the backbone of our DNA are exclusively right-handed. This universal preference, known as homochirality, is a signature of life. But why this bias? In a lifeless, natural environment, any chemical reaction will produce a perfect 50-50 mix of left and right-handed molecules, a racemic mixture. For life to begin, this symmetry had to be broken. One of the most elegant solutions to this mystery originates not on Earth, but in the hearts of interstellar dust clouds. The theory proposes that a special kind of light, known as circularly polarized light, acted as a cosmic filter. Unlike normal light, which vibrates in all directions, circularly polarized light spirals as it travels, either clockwise or counterclockwise. This spinning motion can interact with the mirror image forms of a molecule in different ways. Just as a left-handed thread will only fit into a left-handed bolt, a left spiraling light beam can be preferentially absorbed by, and thus destroy, one chiral form of a molecule over its mirror image. The right-handed version of the same molecule might be completely unaffected by that particular light beam. Now, where could such a specialized form of light be found? It is generated in deep space by the scattering of starlight off of magnetically aligned dust grains in vast nebulae. It is also produced in tremendous quantities by the intense synchrotron radiation whipping around the powerful magnetic fields of neutron stars. Within these stellar environments, immense clouds of gas and dust are being bathed in a constant, one-directional spiral of this destructive light. Over millions of years, this persistent irradiation could have selectively broken down one-handed form of the simple organic molecules forming on icy dust grains. Imagine a vast interstellar cloud where right-handed amino acids are steadily dismantled by a dominant left spiraling light, leaving behind a cloud enriched with left-handed ones. This would create a small but significant imbalance, a slight excess of perhaps 1 or 2%, before these molecules were ever incorporated into comets and asteroids. When these celestial bodies later bombarded the early Earth, they would have delivered this pre-made chiral bias. This initial, faint preference could then have been dramatically amplified by the processes of early life. A self-replicating molecule like RNA, trying to use a mix of left and right-handed building blocks, would be terribly inefficient, like trying to assemble a machine with screws that sometimes have reverse threading. Any system that stumbled upon a way to use just one-handed form would have had a massive competitive advantage, replicating faster and more reliably. Through this natural selection, the slight interstellar bias could have been locked in and magnified across the entire planet, eventually leading to the homochiral life we see today. This theory beautifully connects the largest scales of the universe to the most intimate details of our biology, suggesting that the left-handedness of our amino acids might be a permanent record of light that spiraled through a nebula billions of years ago, a ghostly fingerprint from our cosmic cradle. But this chemical bias was only half the battle. To build a living cell, you need more than just the right-handed screws and left-handed bolts. You need a power source to drive the assembly. Deep within the volcanic landscapes of the young Earth, a pungent, reactive element was waiting to provide that very spark. This is the world of sulfur-based high-energy intermediates. Sulfur is a chemical anarchist. It readily forms unstable, high-energy bonds that are desperate to break, releasing a burst of energy in the process. In the steamy, sulfur-rich environments around volcanic vents and hot springs, simple sulfur-containing compounds could have acted as the universe's first batteries. The key player in this drama is a molecule called a thioester. Imagine a standard chemical link like the bond that holds an acid group to another molecule. Now replace the oxygen atom in that link with a sulfur atom. This simple substitution creates a thioester, and it completely changes the molecule's character. That sulfur-carbon bond is a loaded spring packed with energy and highly prone to breaking. When it does break, it releases that stored energy, which can then be harnessed to power other, more difficult chemical reactions. Specifically, it can drive what are known as condensation reactions, the fundamental process of building life's large molecules. Every time two amino acids link to form a protein, or two nucleotides join to build a strand of RNA, a water molecule is kicked out. This is a condensation reaction, and it requires an input of energy to happen. In your cells today, that energy comes from a universal currency called ATP. But on a prebiotic Earth, there was no ATP. Thioesters could have been the primordial stand-in. A thioester could react with a simple organic molecule, transferring its high-energy sulfur group and activating it, making it far more likely to form a bond with another molecule and release that water. It was a chemical handoff, a way to pay the energy cost for building complexity. This is not just a theoretical idea. Strikingly, the core metabolic pathways that power every single cell on Earth, the citric acid cycle, is fundamentally based on thioester chemistry. The most important energy-carrying molecule in this cycle is a thioester. It is a living relic, a molecular fossil suggesting that our most ancient biochemistry was built upon a foundation of sulfur. Before there was a genetic code, before there were cell membranes, there could have been a simple, sulfur-driven chemical engine churning away in a volcanic pool. This engine would have used the relentless energy of thioester formation and breakdown to stitch together the first polymers, fueling a slow but steady march from chaotic chemistry toward the ordered, energy-hungry world of biology. The profound fragility of RNA points toward a deeper truth, that our search for the first genetic molecule might be looking in the wrong place entirely. An intriguing alternative suggests that before the RNA world, there was a different system, one built from a hybrid molecule that blends the lines between protein and genetics. This is the PNA world hypothesis. PNA stands for peptide nucleic acid, and it is a molecule that feels almost like a scientific chimera. Its backbone is not made from the complex sugars and phosphates of RNA, but from simple, robust peptides, the very same class of molecules that form protein. Yet, sprouting from this peptide backbone are the same nucleobases, the same information-carrying letters found in DNA and RNA. This simple structural shift has a monumental consequence. A PNA strand can coil around a counterpart of RNA or DNA, forming the famous double helix and pairing its bases perfectly, just as if it were a native strand of genetic material. It speaks a universal chemical language. The hypothesis proposes that PNA, or something very much like it, could have been the foundational genetic system on the early Earth. The argument rests on simplicity. The sugar-phosphate backbone of RNA is notoriously difficult to assemble without biological help. Its components, ribose sugar and phosphate groups, are hard to form sustainably and tend to be unstable. A peptide backbone, by contrast, could have been built from the amino acids that were likely abundant in the primordial soup, forged by lightning, impacts, or deep-sea vents. The chemical bonds that link amino acids into chains are more straightforward and stable under a wider range of conditions. In a warm, tidal pool cycling between wet and dry phases, peptides could have polymerized far more readily than the delicate nucleotides of RNA. PNA presents a compelling pathway, a potential missing link. It suggests that genetics could have begun with a sturdier, more easily formed molecule, one that used a protein-like structure to carry genetic information. This PNO world would have been a time of simpler replication, where these hybrid molecules stored and copied data. Eventually, this system could have given rise to or been outcompeted by the more versatile RNA, which then paved the way for DNA and proteins. It is a theory that elegantly sidesteps the greatest chemical hurdles of the RNA world, proposing that life's first blueprint was not written on the complex parchment of RNA, but on the simpler, more durable slate of a peptide. These microscopic dust grains are far more than simple specks of cosmic dirt. They are nature's most prolific and widespread chemical laboratories, operating on a scale so small it defies imagination. Drifting through the vast darkness between stars, each grain presents an immense surface area relative to its tiny size, a sprawling landscape for atoms and molecules to meet. Their surfaces are not uniform either. They are composed of a diverse mix of silicates, carbon, and metals, each mineral offering a unique catalytic property, a different tool for the universe's chemical toolkit. The most fundamental of all cosmic reactions, the formation of molecular hydrogen, relies entirely on this process. A single hydrogen atom, the most abundant element in the universe, is a lonely wanderer. But when it drifts onto a cold dust grain, it becomes trapped, stuck to the surface by weak forces. It sits there, waiting. Soon, another hydrogen atom arrives and sticks nearby. The solid surface of the grain now does its magic, acting as a platform that allows these two atoms to shuffle together and combine, forming a stable molecule of hydrogen gas. Without these dust grains, this essential reaction would be incredibly slow and inefficient in the empty void of space. But the chemistry does not stop with hydrogen. The same process builds toward life's ingredients. A carbon monoxide molecule might stick to a grain. Then, a hydrogen atom arrives and with the grain's help attaches to it, beginning a transformation. Through a series of such surface-mediated steps, simple sugars can form. One of these, detected in interstellar clouds, is glycolaldehyde, the simplest sugar molecule and a direct precursor to ribose, the sugar that forms the backbone of RNA. This is not a chaotic, random process. The ordered crystalline structure of the mineral surface guides the reactants, holding them in the perfect orientation to bond, lowering the energy required for the reaction to occur. It is a form of molecular matchmaking orchestrated by the dust itself. This means that the journey to chemical complexity, the very first steps toward the molecules of biology, did not begin on a planet. It began on these trillions upon trillions of tiny, frozen platforms, silently conducting their chemical symphonies in the dark. The galaxy is not empty. It is filled with these nanoscale factories, each one a testament to the universe's innate drive to build. While the deep sea vents provided a protected chemical haven, they may have also offered a unique source of light. Crystalline surfaces of zinc sulfide, known as the mineral sphalerite, would have precipitated in abundance around certain hydrothermal vents where zinc-rich fluids met the hydrogen sulfide billowing from the Earth's crust. These were not dull, dark rocks. Zinc sulfide possesses a remarkable photochemical talent. When bathed in the faint, penetrating glow of ultraviolet light from the sun, or even in the geothermal glow of the vent fluids themselves, these crystals become incredibly efficient catalysts. They can absorb that light energy and use it to power a specific, vital chemical transaction, the reduction of carbon dioxide. This process takes the inert, oxidized carbon from CO2 and, by adding hydrogen, transforms it into more reactive, reduced forms like formaldehyde and other simple organics. Think of the zinc sulfide crystal as a primordial solar panel. It harvests the faint light filtering down through the ocean and uses that energy to drive carbon fixation, building the very scaffolds of organic molecules from the simplest raw materials available. This is not photosynthesis as we know it, but a purely mineral-driven photochemical precursor. The surface of the crystal provides a perfect, orderly template where carbon dioxide and hydrogen molecules can be held in just the right position for the light-driven reaction to occur. In this zinc world, the first steps toward a metabolic cycle were not powered by heat or chemical gradients alone, but by light captured and utilized by a non-living crystal. It suggests that the foundations of biochemistry were laid on surfaces that could not only concentrate ingredients but also actively power their assembly, merging the concepts of a sheltered nursery with an energy-harvesting technology that predated life itself. That same crackling energy of a lightning storm could manifest in a far quieter, more persistent form. While a single lightning bolt delivers a catastrophic jolt, the atmosphere of the early Earth was likely humming with a softer, more pervasive electrical phenomenon known as corona discharge. Imagine the sharp tip of a volcanic rock, the crest of an ocean wave, or even a single blade of grass in a storm-charged environment. In a high electric field, the air around these sharp points doesn't break down in a single violent flash. Instead, it glows with a continuous, faint electrical aura, a sustained whisper of energy. This is corona discharge, a silent, efficient generator that could have run for hours or even days, far outlasting any thunderstorm. Instead of a single, destructive blast, it provides a constant, gentle drizzle of electrons. This steady stream of energy is perfect for chemistry. It can nudge simple gases like methane, nitrogen, and carbon dioxide into reactive states, encouraging them to link up into more complex organic chains without the violent fragmentation that a lightning strike might cause. Think of it as the difference between a blacksmith using a giant, single hammer blow and a watchmaker using a set of delicate, precise tools. The blacksmith might forge a rough bar of iron, but the watchmaker assembles the intricate gears of a timepiece. Corona discharge is the watchmaker of atmospheric chemistry. Laboratory experiments have shown that simulating this process reliably produces a rich variety of organic molecules, including amino acids and sugars, often with higher yields and greater diversity than experiments using spark discharges alone. This means the entire planet could have been one vast, quiet chemical reactor. Every rocky outcrop, every crashing wave, every bit of terrain on the young continents might have been tipped with this faint electrical glow, methodically building the inventory of life's building blocks and washing them into the waiting oceans with every rain. It suggests that the foundation of biology was not laid only in rare, dramatic events, but in a planet-wide, patient hum, a background electrical song that filled the air with the promise of molecules to come. But these intricate backbones for RNA and DNA demand a very specific sugar, ribose, and its formation presents one of the most stubborn chemical puzzles. How could such a complex and delicate sugar arise spontaneously in the chaos of the early Earth? The answer may lie in a deceptively simple reaction discovered over a century ago. The foremost reaction is a chemical cascade that begins with formaldehyde, a molecule we know can form in interstellar space and around hydrothermal vents. When formaldehyde is mixed with a basic catalyst like lime water, it undergoes a remarkable transformation. It starts linking copies of itself together, building chains that then rearrange into a complex mixture of different sugars. In a laboratory flask, this reaction is a sight to behold. A clear solution of formaldehyde can, within hours, turn a murky yellow and then a deep amber, producing a sticky syrup containing a myriad of sugar molecules, including ribose. It seems like a perfect solution, a one-pot recipe for creating the very backbone of genetics from the simplest of cosmic ingredients. Yet, for all its promise, the foremost reaction is a messy and frustrating process. Its greatest strength is also its fatal flaw. It is entirely non-selective. It does not carefully craft a single molecule of ribose. Instead, it produces a chaotic chemical zoo of dozens of different sugars all tangled together. Ribose is just one member of this unruly crowd, and it is a particularly fragile one. In the same alkaline conditions that create it, ribose is highly unstable and rapidly breaks down. Even if it did form, it would be lost in a sea of other useless sugars, with no clear way for life to pick out the one precious molecule it needed from the chemical noise. For decades, this problem seemed insurmountable. How could a process so chaotic and destructive have given rise to the precise foundation of life? The breakthrough came when scientists began to ask if nature had a way to tame this reaction. They turned to the very minerals that were abundant on the early Earth. Certain clays and other silicate minerals possess surfaces with specific structures and chemical properties. When researchers run the foremost reaction in the presence of these minerals, something extraordinary happens. The mineral surfaces act like microscopic filters and assembly lines. They can selectively absorb and stabilize the formaldehyde precursors, guiding the linking reactions towards specific pathways. Some minerals have been shown to dramatically increase the yield of certain sugars, while others can protect the fragile ribose from degrading too quickly. It is as if the chaotic symphony of the foremost reaction is being conducted by the mineral, its crystalline structure providing a template that imposes a degree of order on the chemical chaos. This does not mean the mineral magically produces pure ribose, but it shifts the odds, creating a slightly enriched mixture where the right sugars are a bit more common and a bit longer lived. In a warm little pond undergoing cycles of evaporation, these mineral catalysts could have repeatedly performed this trick, each cycle concentrating the valuable products and washing away the failed experiments. The foremost reaction, once seen as a tantalizing but impractical dead end, is now viewed in a new light. It was not a perfect kitchen, but a prolific and messy one. And with the help of Earth's rocky, mineralogical toolkit, that mess could have been refined just enough times in just the right places to provide the critical sugars that allowed the first genetic molecules to finally take shape. Yet our planet holds secrets far deeper than its sunlit surface. Buried beneath the ocean floor and entombed within the continental rock lies a realm so alien and expansive it challenges our very definition of a habitable world. This is the theory of the deep hot biosphere, a radical vision proposed by the astrophysicist Thomas Gold. He suggested that a vast, living ecosystem exists within the Earth's crust, a microbial universe thriving in the absolute darkness under immense pressure and scorching heat. Its inhabitants are not survivors eking out an existence, but natives of the deep, living off a food source that predates the sun itself. According to Gold, this deep biosphere does not rely on the organic debris of surface life. Instead, it feeds on abiogenic hydrocarbons, methane, and other fuels that were not formed from ancient biology, but were forged in the planet's very creation. These gases, he argued, were primordial ingredients trapped deep within the Earth during its violent accretion from the solar nebula 4.5 billion years ago. They are a non-biological food source, a cosmic inheritance simmering in the planetary interior. If this theory is correct, it means the first organic molecules, and perhaps the very first life forms, could have originated in this pressurized, pitch-black crucible. They would have emerged completely independent of the sun, of comet deliveries, or of surface chemistry. Life would have begun not in a warm little pond, but in a hot, fractured pore of rock, tens of kilometers underground, powered by the slow, geologic outgassing of the planet's original building blocks. The implications are staggering. It suggests that life on the surface, including all plants, animals, and us, might be a mere afterthought, a fragile, sun-dependent scum on a planet whose true biological mass is hidden deep within its rocky heart. It redefines Earth not as a surface world with a thin skin of life, but as a fundamentally living planet, teeming with microbiology from its crust down to its upper mantle. While deeply controversial, especially among geochemists who largely attribute hydrocarbons to biological sources, the theory forces a profound shift in perspective. It asks us to consider that the cradle of life was not a gentle, sunlit nursery, but a high-pressure forge in the planetary depths, where the first organisms learned to mine their energy from the very rocks that formed our world. The outer solar system holds frozen worlds that hide astonishing secrets beneath their icy shells. Far from the sun's warmth, moons like Jupiter's Europa and Saturn's Enceladus are now prime candidates for the most advanced prebiotic chemistry in our cosmic neighborhood. Their surfaces are frozen solid, a landscape of water ice as hard as rock, constantly bombarded by intense radiation from their giant parent planets. This radiation is not merely a destructive force. It acts as a relentless chemist, breaking apart the simple molecules frozen into the surface ice. As these broken fragments, these molecular radicals, are trapped together in the frozen matrix, they recombine into more complex organic compounds, building a rich layer of prebiotic material right on the moon's surface. But the real magic happens when geology takes over. These moons are not inert balls of ice. They are flexed and heated by the immense gravitational pull of Jupiter and Saturn, a process known as tidal heating. This energy keeps their interiors warm, maintaining vast global liquid water oceans buried deep beneath miles of icy crust. The surface, with its newly forged organics, is connected to this hidden sea through a process called ice tectonics. Enceladus demonstrates this beautifully, with massive geysers of water vapor and ice crystals erupting from fractures at its south pole. These plumes, sampled by the Cassini spacecraft, contain a stunning array of simple organic molecules. On Europa, scientists believe the icy crust slowly churns and subducts, much like Earth's tectonic plates. Sections of the radiation-processed surface ice, now laced with complex organics, could be dragged downward over millions of years, eventually melting and releasing their precious chemical cargo into the dark ocean below. This creates a continuous delivery system. The surface acts as a cosmic laboratory where radiation provides the energy for synthesis, and the moon's own geological activity acts as a conveyor belt, transporting these biological building blocks into a protected, watery environment. Within these subsurface oceans, shielded from radiation and kept liquid by tidal forces, these organics could concentrate in hydrothermal vent systems similar to those on Earth. This theory completely reframes the search for life's ingredients. It suggests that the most habitable places in our solar system are not the rocky planets, but these icy moons where a perfect synergy of radiation and geology works in concert to cook the soup of life in absolute darkness. Perhaps the very first life forms did not need a pre-made soup to feast upon. They may have been master chefs from the very beginning, capable of cooking their own food from the simplest recipe of all. This is the theory of autotrophic origins, a vision where life did not scavenge for organic molecules, but built them from scratch using carbon dioxide as its raw material. The most compelling evidence for this lies deep within the biochemistry of some of the planet's most ancient microbes. They use a metabolic pathway called the acetyl-CoA pathway, and it is so fundamentally simple that it appears to be a living relic, a metabolic fossil from the dawn of biology. This pathway is a direct, one-step method for taking carbon dioxide and converting it into acetate, a fundamental organic molecule. It does not require the complex, looping cycles of modern photosynthesis or respiration. Instead, it relies on a handful of key minerals to do the heavy lifting, specifically clusters of iron, nickel, and sulfur. These metal-sulfur minerals are identical to the ones that form naturally at alkaline hydrothermal vents. The theory suggests that the very first metabolic reactions were not happening inside a cell, but on the surface of these catalytic minerals. A microscopic crystal of iron-nickel sulfide sitting in a warm, alkaline crack in a vent wall could have acted as a natural enzyme. Its surface would have drawn in carbon dioxide and hydrogen from the surrounding fluids. The unique chemical structure of the mineral would have held these molecules in just the right position, using the inherent reactivity of the metals to strip oxygen atoms from the carbon dioxide and replace them with hydrogen, forging the carbon-carbon bonds that are the foundation of all organic chemistry. In this scenario, the mineral surface is not just a passive stage, but an active participant, the original catalyst for life's first energy-harvesting, molecule-building reaction. The first life forms would not have invented this process. They would have learned to co-opt it, eventually surrounding these mineral catalysts with a lipid membrane to create the first true cells. This elegant idea turns the traditional story on its head. Life was not a lucky consumer that found a rich organic broth, but a savvy chemist that learned to harness the planet's own geologic processes to become self-sufficient from its very first breath. Among the many chemical hurdles facing the first RNA molecules, the fragility of their sugar backbone was perhaps the most devastating. Ribose, the R in RNA, is notoriously unstable. In the very conditions where it might form, it quickly breaks down, crumbling before it could ever be strung into a chain. This sugar problem seemed like an insurmountable wall, halting the entire RNA world hypothesis in its tracks. But an unexpected chemical savior may have been waiting in the wings. Boron, a common element, appears to play a crucial and entirely surprising role. Laboratory experiments have revealed a simple but profound interaction. When ribose forms in the presence of borate minerals, the two instantly link up, creating a stable complex. Think of boron as a molecular bodyguard for the sugar. It wraps around the ribose molecule, shielding its most vulnerable parts from chemical attack and preventing it from falling apart. This borate-ribose complex is far more robust, capable of surviving for days or even weeks in conditions that would destroy pure ribose in a matter of hours. This single chemical handshake changes everything. It provides a plausible pathway for ribose to accumulate and persist long enough to be incorporated into the first nucleotides. Where would such a benevolent partnership have occurred on the early Earth? The answer lies in specific and surprisingly common geological settings. Imagine the dried-up beds of ancient lakes or the mineral-crusted edges of hot springs. In these environments where water evaporates and leaves concentrated minerals behind, borates would have been abundant. Here, the chaotic Formose reaction could have produced a fleeting mix of sugars, and the borates present would have immediately latched onto any ribose that formed, preserving it from destruction. These borate-rich basins become more than just chemical factories. They transform into protected nurseries. Within them, the stabilized ribose could have patiently waited, interacting with phosphate and nucleobases to finally, slowly, assemble into the first stable RNA strands. It is a theory that solves one of the most frustrating problems in origins of life research, suggesting that a humble, overlooked element provided the essential stability for genetics to find its first foothold in a chaotic world. Energy never rests, it only flows. The relentless stream of sunlight bathing the early Earth held a deep physical imperative. It had to go somewhere. This leads us to a theory that places life itself as a direct consequence of the universe's most fundamental laws. The thermodynamic dissipation theory frames biology not as a lucky accident, but as a cosmic inevitability. It proposes that the first self-replicating structures emerged as the most effective way for our planet to shed the immense solar energy it was constantly absorbing. Think of the young Earth as a car parked in the sun, its metal skin growing hotter and hotter. To cool down, it must find a way to release that heat back into space. A plain, rocky surface can only radiate so much, but a surface covered in complex, swirling molecules can absorb that light and re-radiate it as heat far more effectively. The more intricate and dynamic those molecules become, the better they are at this job. In this view, the first organic molecules were not just random chemical curiosities. They were the planet's first and most efficient cooling system. The drive toward complexity was not guided by a mysterious biological will, but but by a simple, impersonal physical law, the unstoppable push toward thermodynamic equilibrium. The universe, in its quest for balance, began to build structures that could help it achieve that goal faster. A simple molecule might absorb a little light and release a little heat. But a complex, self-replicating molecule can create countless copies of itself, each one a new machine for turning sunlight into dissipated energy. Life, from this perspective, becomes a spectacularly efficient form of entropy production. It is a runaway process where the most successful dissipative structures are the ones that grow, replicate, and become more complex, simply because they are better at their job of scattering energy. This is a profound shift in perspective. It suggests that the verdant forests, the teeming oceans, and even our own conscious minds are all part of a planetary-scale heat engine, an elegant solution to a fundamental physics problem. The spark of life was not a fragile flame in a chaotic universe, but the universe itself finding its most beautiful and efficient path toward balance. Our journey through these theories reveals a universe teeming with chemical potential, yet a monumental gap remains between a collection of molecules and a living, breathing cell. How did isolated chemical reactions first learn to work together? One speculative but fascinating idea borrows a page from later evolutionary history, applying the concept of endosymbiosis to the molecular world. In biology, endosymbiosis describes how one cell engulfed another, leading to a permanent cooperative partnership like the mitochondria that power our own cells. What if a similar merging of simpler systems paved the way for the very first life? This is the theory of serial endosymbiosis for molecules. Before there were cells, there may have been tiny autocatalytic cycles, small, self-sustaining loops of chemical reactions. One cycle might have been good at producing a specific amino acid. Another might have been efficient at releasing a tiny bit of energy. On their own, these cycles were fragile and limited. But if by chance they became physically linked or found themselves encapsulated together within the same tiny lipid vesicle, everything could have changed. Suddenly, the product of one cycle became the fuel for another. The energy released by one reaction could now power a second, more difficult synthesis. This molecular teamwork would have created a system far more robust and capable than any of its individual parts. It was a chemical synergy where the whole became greater than the sum of its parts. The encapsulation within a simple membrane was the key that locked this partnership in place, preventing the valuable molecules from drifting apart and creating a protected environment where their collaboration could flourish. This is not just a theoretical idea. Scientists have built simple models of this in labs, creating vesicles that contain two or more different catalytic cycles. When these systems are combined, they often exhibit new, emergent properties, stabilizing each other and performing functions that are impossible for the isolated cycles. This theory suggests that the leap to life was not a single, miraculous event, but a series of mergers and acquisitions. It was a form of molecular corporate takeover, where successful chemical enterprises joined forces, pooling their resources and skills until they formed a complex, integrated metabolic network. The first cell may not have been born from a single recipe, but from a successful fusion of many smaller recipes, a grand chemical alliance that learned once and for all how to thrive. This final theory ventures beyond chemistry and into the very bedrock of reality. The anthropic principle confronts a staggering coincidence. The fundamental constants of the universe, the precise strengths of gravity and nuclear forces, the exact mass of a proton, all seem perfectly calibrated. If any one of these values were even slightly different, stars would not burn, complex atoms could not exist, and the universe would be a void incapable of hosting life or even chemistry. This fine-tuning extends all the way down to the formation of the first organic molecules. Why is carbon so abundant forged in the hearts of dying stars? Why do the laws of quantum mechanics allow for such stable and diverse chemical bonds? enabling the intricate structures of proteins and DNA. It appears as though the cosmic deck was stacked from the very beginning in favor of complexity. One interpretation is that we are simply the beneficiaries of an unimaginable cosmic lottery. We exist in this one universe against all odds precisely because its rules permit our existence. This is the weak anthropic principle. It is a statement of selection bias. We are here to observe the universe because it is the kind of universe that allows observers. But a more profound and more controversial interpretation is the strong anthropic principle. This suggests the fine-tuning is not a lucky accident but a necessary feature. The laws of physics themselves may be intrinsically biased, perhaps even designed to produce life and consciousness. When we look at the 30 theories we have explored, from interstellar ice to deep sea vents, a common thread emerges. The universe is not hostile to the chemistry of life, it is saturated with it. The processes that create organic molecules are not rare, delicate miracles. They are robust, commonplace, and operating across every conceivable environment, from the coldest voids to the hottest impacts. This universal fertility forces a question. Is the ease of prebiotic chemistry merely a happy consequence of the universe's physical laws, or is it the entire point? Are we living in a cosmos that was, in some deep and fundamental sense, meant to come alive? This theory does not provide a chemical mechanism, it provides a cosmic context. It pushes the origin of life from a planetary question to a cosmological one. The answer to why we are here might not be found in a test tube or a rock sample, but written into the first moments of the Big Bang itself, a silent, predetermined bias toward beauty, complexity, and mind. We have wandered through a gallery of cosmic possibilities, from lightning in a primordial soup to the silent chemistry of interstellar ice. We have witnessed life's potential spark in the deep sea's warmth, in the violence of asteroid impacts, and even in the quiet, persistent hum of radioactive decay. Each theory, from the elegant RN, a world, to the profound implications of the anthropic principle, is a brilliant beam of light pointed at one of humanity's oldest mysteries. None of them are mutually exclusive, and perhaps the true story is a grand synthesis, a chorus of processes working in concert across the galaxy. The sheer diversity of these ideas reveals a fundamental truth. The universe is not a sterile void, but a master chemist, tirelessly experimenting with the recipe for life in every conceivable environment. This puzzle remains vibrant and unsolved, a frontier where the next great discovery, whether in a lab, a space probe, or a mathematical equation, could be the one that finally connects us to our ultimate cosmic origins. The evidence is mounting that we are part of a universe inherently biased toward complexity. So we turn the question to you. After this journey through 30 possibilities, which theory resonates most deeply? Is our existence a thermodynamic inevitability, a gift from the stars, or a story born in a warm little pond? Share your thoughts on where the first spark truly began.